Today's lecture is part 4 of chapter 8, Compaction and Settlement. Just to remember you, to remind you, what is the difference between compaction and consolidation? We said that there are two types of settlements. We have something called compaction and we have something called consolidation. Usually compaction is related to something called immediate settlement, which is the settlement that will happen very quickly on the spot when I apply the load. This will happen with some types of soil like sand, which means that it happens with cohesionless soil. Consolidation is another type of settlement. It is the settlement that can happen to clay. What is the difference between clay and sand? Anyone remember what was the difference between clay and sand? From previous knowledge, what's the difference between clay and sand? Why do we usually say clay and sand? What is there? Why is clay so different from sand? Particle size. يعني حلو. طب البارتيكل size دي هتأثر في إيه؟ What will be the effect of the particle size? Not friction, but mainly إيه بقى؟ الووتر، الإفكت of water اللي هي بنسميها expelling water outside of the sample. We said that water can carry load, but unfortunately water will not stay all of the time. It will be available at the beginning and it may be dissipated very quickly. In case of sand, in this case I don't have I cannot feel the effect of water because there is water, but once I put the load, water is expelled outside immediately, so it has no effect. But in clay, because of the effect of the particle size and the effect of the motion of the permeability of the clay that is very low, so water will not leave my sample immediately. It will take time. This time will be maybe 1 or 2 hours, and it may be 60, 70 years. It depends on the type of the clay. So this is the difference. That's why we are going to have a lecture for consolidation. It will be a separate lecture because it's different behavior. But now my lecture is dedicated to compaction and settlement. Why I'm speaking about compaction and settlement? It means that I'm speaking about the case of no consolidation. Just I try to compact the soil to get rid of all of the voids that are, not all of the void, but part of the very big portion of the void, so that the remaining is compacted soil. And we gave lots of examples. This was the equation that presented what are all the types of settlement. We said that we have 3 types of settlement. We have this ST, which is the total settlement. The total settlement is the sum of the elastic settlement. This is the first portion, the one that we said that it may happen in sand and it may happen in clay sometimes. So this is called elastic settlement. It happens immediately. Then I have something called primary consolidation settlement. This is the consolidation settlement that we were speaking about. There is another type that we did not discuss now, which is called the secondary consolidation settlement. What is the secondary consolidation settlement? First, compare these two together to eliminate them. Elastic settlement and consolidation settlement. Elastic settlement happens immediately. Consolidation settlement happens after a while. Elastic settlement happens due to a decrease of the volume of the void. Consolidation settlement also happen due to decrease of the volume of the void, but after expelling water outside, so it depends on the permeability of the material. So I'm speaking about motion of the water from inside the sample. So these are the two main categories, elastic and consolidation settlement, which we call primary consolidation settlement. What is secondary consolidation settlement? It's another type of consolidation that will happen at a later stage with a very small portion. What is it? It is something like a redistribution of the particles itself to fit better in the matrix of the material. Maybe a particle would be moved a little bit to the right, to the left, to fit in a better space. So the volume, the total volume will decrease, not because we are expelling air, nor because we are expelling water, but because the shape of the particles itself is being redistributed to fit better into the matrix of the material. So this is the secondary consolidation settlement. I don't just want to repeat all what we said, because you can refer to the recorded lecture, but this was what we discussed about settlement, and we said how to calculate settlement if you have many layers, how to calculate them, and so on. What is the effect of the external load on the soil, and how to calculate this external load, and so on, till we reached this soil compaction. We discussed the soil compaction. This is a figure that I wanted to share with you. This is a soil that it is not compacted, and this is a soil that is compacted. So what happened? The voids, these white spaces, decreased here, and these blue spaces are more or less the same. Why? Because water is still inside. So this is not consolidation, this is settlement, normal compaction that caused settlement. But if I increase the load more, what will happen? All of these voids will be expelled, and I will end up having only voids full of water. So the next step will be only consolidation settlement, and this will take longer time. So once you put the load on the soil, you expel air. So there will be some settlement. This is called elastic settlement. Increase the load more, you will end up reaching a case where all of the voids remaining are full of water. So this is the start of the consolidation settlement. When does it end? Nobody knows. It depends on the permeability of your soil. It may end in few days, or it may end in many years, depending on the material. So it will take time, and with this time, it is consolidating. In parallel to this consolidation settlement, there is something called secondary consolidation settlement. These particles itself may change its shape. The particle, not change of the shape, but the direction. Maybe this portion would go down and this portion would go up, so it fits better in the space and decrease the gaps between the material. So this is the third type, which is the secondary consolidation of the soil. We said something about compaction. We said that in any compaction, compaction means that I'm either compacting the surface of the soil, and this is not very important except for making a layer that I can put my footing on top of it. But what is more important for compaction is compacting layers. If I want to increase the height of the soil from a certain level to another level, maybe I will have to compact to dump, say, 2 2 meters. I cannot just dump 2 meters and go on top of them and compact the surface. No, I have to compact each layer to reach the surface. You have to take into consideration that all equipment used for compaction can only compact 25 to 30 centimeters maximum. So if you dump 2 meters and compact the surface, then you are compacting only the top 30 centimeters. What about the bottom? They are the same. They will not change even if you use a very heavy equipment like this. So what should I do? I should put the soil in layers. 30 centimeters, compact. So the 30 will be 25. Put another 30 centimeter, compact again. And so on, 30 compact, ending up with having, say, 8 layers. Each now is 25 centimeters, and this is very compacted soil, and I can put my building on top of it. So this is something important. And then I think we reached this point. So this was, yes, this was where we are going to start now. Before we start, I'm just giving you these equations. These are good relations that can help me in what I need. What I need is to calculate something called gamma dry. What is gamma dry? Gamma dry is the unit weight of the soil in the dry condition without water. It is a very good measure for the degree of compaction. Why? Refer to this figure again. This figure. If I take this sample, put it in the oven, all of the water inside will be evaporated. It will evaporate. Take this sample, put it in the oven. Also, everything will be evaporated. All the water will evaporate. So, if I tell you I want to take a fixed volume, it means that if this is my volume, then I will take a volume similar to it. You remember that we said that all these particles came closer to each other and became this volume. So if I take the same volume here, it means that I'm going to take away some particles, and I will end up having here less amount of particles than this. You follow me in this or not? This is the big volume. I compacted this big volume. Suppose that this volume is 1.5. I compacted it to be 1. It means that, or say, عشان to be accurate in the good scale, suppose that this volume now is 1.2, and this volume here is 1. But how this happened? It happened by compaction. All of the particles that were included in the 1.2 meter cube were included in the 1 meter cube. It means that this is more condensed than this. If I tell you what is the unit weight of this, will it be the same as this unit weight? Unit weight is what? It is weight divided by volume. The weight here is the same as the weight here, but the volume here is 1.2 and the volume here is 1. So it means that the volume here is less. So if I divide the same weight by a smaller volume, it means that I will get bigger unit weight. Again, or this is clear? Not clear. What is the meaning of compaction? The meaning of compaction, let's have a class. And this class, this is the class. It contains 50 students. And then I brought another 20 students. And then I pushed them inside the class. So the class now includes another 20 students. which class is more crowded? The first one or the second one? The second one, because it's in the same volume. Instead of having 50 students, I had 70 students. So imagine that these particles are the students. These are the 50 students. And instead of adding a number of students, no, I took these 50 students from this class to a smaller class, and I tell them, go into this class. Which is more crowded? It's the same number, 50 students. But the space that will include these 50 students is decreased, so it's more crowded. This is what happens. In soil, I compact. I don't ask the students to go. As if I'm compacting the students. I'm pushing the students to go inside. So now here is number of particles. The same number, due to compaction, was included in a smaller volume. It means that the weight of the soil, the density of the soil will increase. The weight will be the same because it's the same number of particles, but the density increases. You know what is the difference between weight and density? Weight is the full weight, but density is the weight per unit volume. It means that what is important for me is how many particles are there in a specific volume. This is my specific volume, and now I took all of these particles, compacted them in this, so the unit weight here is more. To compare different types of soil, we use something because there may be some water inside, and this water will give me a wrong impression. It may tell me that the weight is more, but it is not really more. It is the effect of water, because here are more water than there, so the water affected. So to compare different types of soil, I use something called gamma dry. What is gamma dry? I take this sample, put it in the oven, all of or most of the water here will evaporate, leaving only particles. I will take these particles, get the weight of them, and this is the dry. This will help me in calculating the dry unit weight. I will take the weight divided by this volume to get the dry unit weight of this sample. What does this help me in? This helps me in knowing the soil. Is it compacted or not? Just if I calculate this unit weight, I want to calculate this dry unit weight compared to this dry unit weight. Which one will be more and which one will be less? Can you concentrate? I have here the same number of particles here and the same number of particles there. So it means the weight is the same. But the volume here is smaller than the volume there. So it means that the dry unit weight of this is bigger than the dry unit weight of this. Unit weight, not weight. Unit weight means the weight of a specific volume. If I take here this volume, then from this I will not take all of the particles. I will take only the particles included in the same volume I have here. This volume, suppose that this is 1 meter by 1 meter. So I will take from here 1 meter by 1 meter, 1 meter by 1 meter, and I will take all the particles inside this, but any particle outside I will not consider it. So if I'm counting the number of particles here, it will be less than the number of particles in this. So the unit weight here is less than the unit weight there. So increasing the unit weight means the soil has been compacted. This is what I want to reach with you now, is that unit weight can be used, dry unit weight can be used as a measure for the degree of compaction. When you have high dry unit weight, it means that the soil is compacted. If you have low dry unit weight, it means that you have soil that it is not compacted enough. So all of these equations give me how to calculate the dry unit weight based on many factors, based on water content, here based on void ratio, based on gamma bulk, which is the unit weight of the soil in the field as it is. So it means that I can calculate gamma dry based on many equations. If I know these equations, these will be my measure to calculate the degree of compactness. This figure is important because it's a relation between the amount of water included in the soil, which is the water content. What is the water content? The water content is the amount of water included inside the soil. It's usually a percentage. If I have, or say 0.2, 0.3, 0.4, it means that out of 1, the amount of water in the sample. So here, when I go in this direction, it means I'm increasing water in the sample. If I go in this direction, this is the dry density, the dry unit weight that I was speaking about now. Increasing the dry unit weight means I have a very good compacted sample type. I will just take many samples with different degree of compactness while adding different amounts of water. It means that I have soil, it's not compacted. I will add some of this water into my sample. What will happen? I will compact. I will give my maximum effort that I can compact the sample. And then I will measure the unit weight. I will take another sample of the same soil, put more water. If in the first time I added a bottle, now I will add 2 bottles. And then compact again. And then another sample, put 3 bottles, 4 bottles, 5 bottles, and so on. Every time increase the amount of water in the soil, and every time compact and measure the dry unit weight. How I measure the dry unit weight? I will take the sample after compaction, put it in an oven, get rid of the water, so what will remain is the particles itself. Get the unit weight of this soil, it means this will give me a measure for the degree of compactness. So you will find that the curve that I'm going to draw is having a bell shape like this. It means that when I increase the amount of water in the sample, I can compact the soil better. Why? Because water will act like a lubricant. Water inside the particles is lubricating the particles. So I'm getting my hammer and trying to compact the sample. If the sample is lubricated, it will be easier for the particles to fit nearer to each other. But if the soil is dry, it will be very difficult. So once I add water, particles come nearer to each other, so the unit weight, the dry unit weight will increase. So I will start with this sample, add water, the unit weight will increase. Add another water, the unit weight will increase. Add more water, the unit weight will increase. Then it would reach a value. If I add more water, I find that the unit weight is not increasing, it is decreasing. Why? Why at the beginning, when I'm adding water, it was lubricating the particles and being compacted better. But when I reached a certain value, adding more water decreased the unit weight, and it started to decrease. Because if I refer to this figure again, here, this figure, if I add water and I start to compact, the particles will get nearer to each other till it reaches something like this with all the voids full of water. If I add more water, where is this water is going to go? It has no space. It will push the sample, the particles away from each other. It will start to increase the voids inside. So when I take this sample with the increased voids that is full of water, and I take it to the oven and get rid of the water, then what will remain is soil with low density, because particles were pushed away from each other. So at the beginning, adding water improves the performance of the compaction till I reach the maximum. I cannot compact this soil more than that. Once I reach this point, the unit weight decreases, and so on. So it means if I do this test at the lab and I know this volume, this amount of water, and I go to the same site and I want to compact the site, what will I do? I will tell the people there, add a specific amount of water to the site equal to this amount, because this is the best amount of water that will let you end up with having a very good compacted soil. If you increase the water, you will get lower compaction, because the water will push the particles away from each other. If you decrease the water, you will have problem in compacting the soil. So this is always my target. So this is called optimum moisture content, OMC. OMC is the optimum moisture content, is the moisture content of the soil where I can get the best compaction for this soil. If I go in the dry side, which is lower amount of water, I will have difficulty in compaction. If I go to the other side, I don't have difficulty in compaction, but the water I'm adding is pushing the particles away from each other, so it is removing part of the compaction that I have done at the previous stage. So this is my target. But can I do this really on site? Can I tell people just go to this point? No, I usually give them, I can work, say, if this is 100% compaction, maybe I can reach, say, 79%. So I take 3% plus and 3% minus, and I can tell them on the site, you can work between these amounts of water. Add this or add this, you will have good compaction. Okay, so I just give them the target of the optimum moisture content, and I can expect, it's not for me, if I do some quality control, I will not ask them for 100% maximum dry density. I can accept less by 2 or 3%, or maybe 5%, depending on the case. Here is the definition of the wet side and the definition of the dry side. This is the dry side and this is the wet side. Okay, this is the concept. This is my concept of compaction, how I measure this compaction. What do I do at the lab? I do a test. What is this test? Similar to we studied before, the direct shear, which is a test that is conducted at the lab. There is another test that is conducted in the lab. It's called the standard Proctor test. The standard Proctor test, by the way, it is in our lab. You can see it if you want. This standard Proctor test is a measure for the compaction of the soil. How I will take the soil compacted with a specific effort so that I get a special degree of compaction. Take this sample, put it in the oven, expel all, let all the water evaporate, then take the dry unit weight of this sample. This will be an indication for this compaction of this for this sample. How? I'm not going to go deeper into the details of the test, but it is all of it. It is written. This is the sampler, or the place where I put my sample. This is the equipment that I'm going to use for compacting the soil inside. It's something like hammering the soil with a weight so that it would be compacted. Of course, I should use a specific effort. Say I will compact it 25 times. And I will do this on layers. I have to be specific on how to compact the layers, so that if I take a sample from one soil and a sample from another soil, both would be compacted with the same effort. It's not the type of soil changes, but my effort for compaction is the same. So if I tell you that the standard Proctor test for sand, for silty sand, is different from sandy silt, it is because what? Because of the type of the soil, but the degree of compaction is the same for both samples. This is the shape of the sampler. This is the dimensions, the weight, everything. It is written here. This is the mold where I put my sample inside. Everything is written, but I don't want you to memorize it. I just want you to understand that this is the concept of the test. A mold, I fill it with soil. I compact it using this compactor to a specific effort. Once I finish, I just dry it and then measure the unit weight. This is the test procedure. You can read it. Once I finish this test for one sample, I do it for many samples at different water content. Every time I add water content in a different way. And then I draw this curve. When I draw this curve, can anybody from you tell me what can I get out of this curve? If I manage to do this test 1 times, 2 times, 3 times, 4, 5, 6, 7 times, and then I draw this curve. This curve is a relation between the dry density or the dry unit weight compared with the water content that I have added. What will I? If you get this curve, what is the importance of this curve? What did you get out of it? Can you understand? From what I said before, in this, it's a similar one. From this one, I got the same here. This is the same shape. What does this mean for me? What is important to get out of this curve? Pardon? Yes, the water content. That here is the water content, which I call the optimum moisture content, that is related to the maximum dry density. It means that if I use for this type of soil this amount of water, I will get the best compaction for this soil. So it means that if you go to a site and they tell you, we want to compact this site, you tell them, okay, give me a sample. Take this sample to the lab, give it to the lab. The lab will take this sample, take from it these 7 specimens or whatever number of specimens they will take. They will perform the test 7 times, and then they will draw this curve. Once they draw this curve, they will tell you to compact this soil very good. Take this value to be your optimum moisture content, add it to the soil, and compact the soil, you will get the best value. Okay. Suppose that they use this optimum moisture content and they compact the soil, they were supposed to get this value for the dry density, but unfortunately they did not get this value. They got lower values. Why? Because soil is not homogeneous. Soil is not the same everywhere. It changes from one. Maybe you took a sample from one location and you now are compacting the full length. It's not the same. So you have to give them some tolerance. Don't expect that you are going to get 100% compaction. No, don't expect this. You say that I will accept till 95%, till 75, till 85. So according to your specs, the specification you are going to use, maybe it is 97%. So from this number, I go below here to 97, I go horizontally, I will cut the curve in 2 points. So these 2 points, in any point along this curve, is accepted. I can accept. Of course, I will be targeting to use this optimum moisture content, but I'm not going to use less or more. No, I'm targeting to use this, but practically, I'm not always reaching what I target. So I will accept any dry density within this 97%. This is a comparison between something called standard and modified Proctor test. We were here discussing something called standard Proctor test. Standard Proctor test is a test, is the test that we have just discussed. What is modified Proctor test? It is the same. It is Proctor test also. It is the same test, but with a different amount of compaction. The degree of compaction is different and the percentage of water is different. So it is another test. Why do we have another test? It depends on the case. Some tests are better with the standard, some tests are better for the modified. Of course, they started with the standard and then they added the modified Proctor test because obviously it is better for some cases in our test. Of course, this is the rest of the test, and then I will reach this curve, and this is what is the difference between the two, the standard Proctor test and the modified Proctor test. Here they say that the number of layers, if you get the sample, here in the standard you have 3 layers, in the modified you are going to use 5 layers. Hammer weight, the hammer weight is here 2.5, here it is 4.5. So I am using higher compaction effort. Falling height, here it is falling from 30 centimeters, here it is falling from 45. So I am using bigger weight and falling from bigger height, so I'm putting more pressure on the soil. How many blows? It's 25 for both. So I'm just compacting it 25 times. So of course, I just want you to know that there are 2 types, modified and Proctor test. The modified Proctor test and standard Proctor test. This is all what you need. This is the difference between the two. It has nothing to do with the equipment. Everything is the same. The difference is in the procedure itself. What is the weight that I'm going to use? What is the height for the hammering, for the hammer to fall, and how many layers I'm going to compact, how many layers that I'm going to compact. This is just a presentation. We said that, you remember that this was the result of the Proctor test, the standard Proctor test. Suppose I do for the same layer, for the same soil, a standard and a modified Proctor test. And I want to put both on one chart. This is how it would look like. This is more or less what you have seen here. This is as if that this is the result of the standard. So I'm going to put this here, then this is the standard test. If I repeat the test with the modified procedure, I will get this curve. What does this mean? It means that the difference between the modified and the standard is that the modified, because it have higher effort, so it reached a higher degree of compaction. Gamma dry maximum is here say مثلا it is 18.5 compared to 16.5. So the gamma dry maximum increased because I used higher compaction pressure. In the same time, I did not need high water content. So I used lower water content, and with the high pressure, I used better. It is better for me always to replace the amount of water with higher compaction pressure. So for the modified Proctor test, the pressure for compaction or the effort for compaction is higher to reach a higher gamma dry. This is all what I want you to know. Maybe I will just check something. Here is something called zero air voids. If you remember, when we draw this and this, what was the difference? The difference was in the effort of compaction. Here I exerted more pressure on the soil to get this one. Suppose I want to draw another curve for another case, but with lower compaction pressure. I expect that the curve will be here. If I put another curve with higher compaction pressure, the curve would be above here. So if I just put all of my curves in one curve here, this is a very low compaction pressure, this is higher compaction pressure, this is much higher compaction pressure, and so on. You find that you can draw something here, a line here, that is more or less the trend line of all of these lines. It is something like a line that we expect that it means that it's something imaginary. Zero air voids, it means I compacted the soil, expelling all the voids, no voids in this. Of course, I cannot do this because to expel all the voids, it means all my particles would be fitting next to each other with no voids in between. This is something imaginary, but in case I reach this imaginary case, in case of getting this, I will get something like this line. This will be my case. I just want you are not going to use it in anything, but I want you to know that zero air voids is the curve, but it has a shape of similar to a line. This curve, it represents the case of increasing the water content with the corresponding dry density, but reaching a case where I have zero voids. This will be my curve. That's all. What I want you to know about this ZAV or ZAV curve. There is something, I said it inherently now, but how can I measure the compaction? I compacted a land here and I compacted another land here. I will take a sample from here and a sample from there. What should I test to see which is compacted better? I should do something called or check something called the relative compaction. The relative compaction is gamma dry field divided by gamma dry maximum. Where is gamma dry maximum? This top portion. If I have this red curve, I go horizontally, this is the gamma dry maximum. This is the maximum dry density that my sample can reach. Suppose I have a sample here at this point. and here is the maximum. What is my degree of compaction? I am here at this point, and I should have reached this point. So if I divide this by this and I multiply it by 100, I will get the percentage of my compaction that I have conducted. So gamma dry maximum is the maximum dry density of the sample in the field compared to what I have in the lab at the top of the curve. This is just here. Let me read here. This one. This is the maximum that I have in the lab. I could not reach more than that. This is the maximum dry density. But suppose I get a sample from the lab, from the site, and I measure the dry density, and it is something here in this at this location. So it means that the degree of compaction is just the relation between these two values. So this is what we need to just to put here, that this is the relative compaction is the gamma dry field divided by the gamma dry maximum at the lab multiplied by 100. It should be usually between 95 and 98%. 100% is impossible. Less than 95%, it is not compacted good. So I have to be usually between these two. It depends on my foundation. If I have a foundation of a very, very special structure, I will recommend 98%. If I'm having a road, I want to compact it, maybe 95 is enough. So it depends on what I'm building on top of this compacted soil. Is it the foundation of a very important structure, or just you are doing a road for the cars, or maybe a road for people to walk? So it depends on the importance of your structure. This is an example. What you expect to get out of me? You are going to, I took one sample, took from it many specimens, added water with different percentages, conducted the test either modified or standard Proctor, and each time I measure the gamma dry. So I expect that I will have something like this. It's a curve. This curve says that when you increase the water content, the gamma dry increases till it reaches the maximum, and then it starts to decrease. Just a reminder, why does it decrease? At the beginning it was increasing because the water was lubricating the particles, so it was easily compacting. With the same effort, I'm compacting better. But when I reached a certain limiting value where my sample was compacted to the maximum, all of the voids are full of water. So if I add more water will go inside, push the samples away. So it is decompressing my samples, my compressed sample. So it is reducing. Now water started to be not a benefit. It is destroying what I have done at the beginning. So it starts to push the samples away, so the density decreases. So from this table, I will just draw these lines. Of course, he is not giving me gamma dry in the example, just to make the example a little bit complicated. Instead of giving you gamma dry, I will give you gamma bulk. What is the difference between gamma dry and gamma bulk? Gamma dry is the unit weight of the sample after being taken from the oven without any water. But gamma bulk is the way it came from the site. As it is, I will just measure the density or the unit weight. Is there a relation? At the beginning, you remember I gave you a few equations. I told you that these equations are very important because they can change from any state to calculate my gamma dry. So here, gamma dry, I will use this equation. It is equal to gamma bulk divided by 1 plus water content. I have the water content and I have the gamma bulk. So I can use this equation because it serves my purpose. And then, so I will substitute with these two in this equation to get this gamma dry, and so on for all of these lines, for this line and this line. Then I will draw a chart between the water content and the gamma dry, not the gamma bulk. So this will be my required. If they tell me that I am expecting that you will reach 98% compaction. What does 98% compaction means from what we said? This is the 100% compaction. 98 is 98% multiplied by this value. See, so if this is 18.15, the 98 will be 17.79, and I will just get the water content that is related to both. So this is the range of water content, but of course in compaction I should not use this range. I should always target this range, this one, because this is my optimum. But usually, as I said, water, soil is not homogeneous, so maybe water will be increased at some locations, decreased at some locations. So the final is that I will accept anything with this range of gamma dry. You should read this. This is an example. This example, you have many factors, and you are required to calculate the unit weight of soil and the dry unit weight. Of course, to calculate any of this, you can calculate it using equations. You will just get the equation of gamma dry and the equation of gamma bulk. I need the weight of soil, the volume of soil. It is given here in this test. So you can just divide them together to get the gamma bulk. So you know now that gamma bulk is the weight of the soil divided by the volume of the same soil. This is gamma bulk. But gamma dry is different. Gamma dry is gamma bulk divided by 1 plus the water content of the soil. Just normal, it's not a very difficult example. Just substitution in an equation. We'll stop here, and next time we'll start with the method of compaction. It will be easier because it is just lots of figures and lots of. In the previous one we had, it was the most difficult part of the lecture, but the other part, inshallah, it will be easier. Thank you.